Hello everyone. So welcome to my live stream again. So in the today's live stream, I'm planning to mix both the system design as well as the uh, lead coding concepts, just to avoid boredom for myself. When I was doing system design interview prep, it was uh, it was little overwhelming in terms that most of the things that I read about feels pretty obvious after working for so many years, but but still I think there is some room for improvement in terms of how we can organize the thoughts and present within that given time. In our real time experience, uh, if the scheduled time doesn't work out in a design review meeting, then basically we tend to schedule another meeting, and then we address the points that were not addressed in the initial design. But that doesn't happen in the interview. In the interview, we need to provide all the trade-off and all the context and the complete picture of the design that we are providing. So it is good to practice the concepts. So let's dive in without delaying it. So the way I'm thinking of going about this one is I will be studying at the same time. I'll be making a note, and the most useful thing that I'm expecting out of this is the summary. I will summarize each of the topics that I would study once I go through the um, go through the materials. So that way it will be much more useful for everyone. So let's start now and see where we will get. And in between, if I have to schedule some quiet time to study, what I'll do is I'll try to uh, try to have the blank screen, and then I'll focus on study, and I'll be updating the notes, or I'll just expose the notes as another window. Yeah, let's get started. If you have any questions, feel free to post it, and also I'll be posting this important links or to follow along if um, someone wants to study with me or prepare with me and use the same materials. Then okay, I've been posting those links. So currently, let's start with designing a pastebin. So I have posted the link for the GitHub repository and my notes that I'm making while following along. So I had started it little bit. So I will start from the previous version. So I started by capturing the functional requirements here. So in this system, while designing a pastebin, the functional requirements, most of the functional requirements are the user should be able to enter some text and generate a random link out of that text, or generate a random link for the viewers to see that text. And then each of those paste links should have an expiration. So by default, we will provide that, okay, it will never expire, but the user should be able to configure an expiration. And user should be able to paste the URL and view the contents that is on the reader side, not the one who create the paste. And also user can view it by staying anonymous. What I meant to say was user login or registration is not shouldn't be necessary. And service should delete the expired paste URLs once the expiration date is there, or expiration time is complete. And paste supports only text only content. So that's it. And for the non-functional requirement, usually this is a collaborative exercise, and during the interview we talk to the interviewer. If I mean, all the positive experiences for me in system design rounds has been more collaborative. uh, Irrespective of the result of the interview, it feels like you learn something out of it, or it feels like a positive exercise if the interaction is more collaborative. But at the same time, if you are the only one who should talk during the interview, it makes your life difficult if you have to talk for 30 minutes or more continuously without getting a lot of feedback from the other side. So in this case, I'm assuming that these are the requirements, and the interviewer is agreeing with these requirements. So let's come back to this one. So as non-functional requirements, the service should be able to track the analytics, and service should have the high availability, and traffic is evenly distributed. These are certain non-functional requirements, or the constraints or assumptions that we are making. You can see here, like it is given as like use cases and out of scope and constraint and assumption. I have classified it to uh, functional and non-functional requirements. And then the out of scope, it's better to state what is out of scope and what things are not addressed during the system design as well. So the user registration and visibility mode of the paste link, and custom link or a custom URL, those things are out of scope uh, for this design. And then back of the envelope calculations for this one, let me see. Okay, for back of the envelope calculations, let's make this as okay. So in the calculations here, there are few of the requirements that are given. So or the assumptions that we get it clarified from the interviewers, like traffic is not evenly distributed, following a short link should be fast, and custom URL. Yeah, and paste or text only. Page view analytics do not need to be real time, and 10 million users, 10 million paste writes per month, 100 million paste read per month, 10 is to 1 read to write ratio. Okay, and then calculate the usage. Calculate the usage. So here the size of the paste, they have given a rough estimate here. Size of the paste is like the text will be 1 KB approximately, and then the short link can be 7 bytes. Expiration rate, expiration link could be somewhere like a 4 or 5 bytes, and created at is 5 bytes, and the paste path should be like should take 255 bytes. So including all these, it should be approximately 1.25 kilobytes. So if we make that assumption, for a single record of the paste bin, so or a single record of a paste, if it takes 1.25 kilobytes for per month, how much storage that we need per month, they have told we would create 10 million pastes per month. So that would make it like 1.25 KB multiplied by 10 million. So that would be 12.7 GB per month. Okay, let's follow a single convention, this KB. Okay, so that should be 12.7 GB. And then by calculation, so this one is a good assumption I read from this content here. It's a handy conversion guide. 2.5 million seconds. How many seconds are there a month? Approximately there is 2.5 million seconds per month, and I'm sure they might have calculated it by um, every day. Every day in the month, let's say 30 multiplied by has 24 hours, multiplied by 24 hours, and hours will have 60 minutes, then 60 seconds. Okay, so let's see what this one would give. The calculation of this one is okay. So this is this value. Okay, there are this many seconds. So this means this is, yeah, 3 3. So it is equivalent to approximately 2.5 million seconds per month. Wow, that's a huge number. So yeah, with this thing in mind, what we can calculate is they have given approximately 10 million page writes per month. So that means every second there might be four paste, so four write requests per second, and then there is 100 million page reads per month. So 100 by 2.5, so that should be 40 read requests per second. So this is the basic calculation that we can come up with. So next thing is creating a high level design. So we can use these things if use these numbers in our design if we think this can become bottleneck at some point of time while we handle the design. So next thing is creating a high level design. So in step 2, so this is all step 1, what they have captured it as. Step 1, they have captured it as outline use cases and constraints. So once the use cases and constraints are gathered, let's do a high level design. So create a high level. So in the high level design, I think this pretty much is the uh, generic component diagram for most of the services that we would handle. Everything will have a client, everything will have a web server that it connects to and then reads certain data from a database. So this is like a generic one. And then from the database, after the data, we can derive some analytics using that data. So even if we are designing something like an Instagram, or if we are designing something like YouTube or anything, the same model should follow. It will have a client, it will have a server, and it will have have the APIs supported from that server, and then the data, and then those services will be backed by some database, and after that we can draw analytics from the data that we store or retrieve from there. So yeah, this is pretty generic. I do not see a necessity to capture it, but in the interview we can start from here, and then we can elaborate. Okay, we are handling the web server, but if we want to make it distributed, how will we handle that scale? And if we want to write API and read API, but we want the read we want an exclusive read replicas in the database, how we would handle it. And then if we assume that okay, reads are getting delayed because there are a lot of traffic, and I don't anticipate the data to be changed so quickly, or I do not need the change to be reflected so soon, then we can add a caching layer. Things like that, we can make those informed decisions, and then keep improving our system design. Let's see, step 3, after once we have the high level design, there is nothing spoken about it because it's pretty generic. We can design the core components. So here I think just for the sake of it, I'll have this image copied and pasted here. But yeah, I feel that it is pretty generic and would not doesn't provide a lot of value. So let's do this. So this one. Okay. Okay. So the next step would be to design the core components. So that would be an important step. So here. So if we are going through step by step, and if we want to address all those steps or in the interview, if we strive to address those within the given time, at least we will have a holistic design by the end of the allocated time. So at least we should target for that one. So outline use cases and constraints. So after today, or maybe like once I get comfortable with the basic cases, I'll try to have the timed exercises instead of just going on and on with this for a long time. Okay, so I like the structure here. It's going good. So step 3, now we need to design the core components. So this read later can go before this system design so that we have enough data for this. Okay. So we have this design core components now. That's the important step. Let's see what they have mentioned. Gather the requirements and scope the problem. Ask to clarify use cases and constraint, discuss assumptions. Without an interviewer to address clarifying questions, we will define some use cases and constraints here. Use cases will scope the problem to handle only the following use cases. User enters block of the text and gets a randomly generated link. Okay, expiration, default set. Okay, these are outlines of use cases, and this one we needed to get to the design core concepts, core components. Let's see, dive deep into dive into the details of each core component. So these are the core component. Dive into the details of each core components as we discussed. Use cases. User enters a block of text and gets a randomly generated link. We could use a relational databases as a large hash table, mapping the generated URL to a file server and path containing the paste file. Instead of managing a file server, we could use a managed object store such as Amazon S3 or NoSQL document store. An alternative to relational database acting as a large hash table, we could use NoSQL key value store. We should discuss the trade-offs between choosing SQL and NoSQL. The following discussion uses the relational database approach. Okay, so let's look into these key terms. We could use a relational database as a large hash table. So let's see what is it. First thing, relational database management system. A relational database like SQL is a collection of the data items organized in tables. ACID is a set of properties of relational database transactions: atomicity, consistency, isolation, and durability. So each transaction is all or nothing. Basically, if we are not able to perform all the operations within a transaction, then none of the operations will be performed. All of those things will be rolled back. And then consistency. So that means all the replicas or all the users would be able to see a single version of the data. Like it won't be like multiple users while querying at the same time would say would see some delay in the replication or would see some different versions of the data. And isolation. Okay, any transaction will bring the database from one valid state to another. Okay, isolation. Executing transaction concurrently has the same result as if the transactions were executed serially. Okay, concurrently and serially. So that means every individual transaction should be isolated from each other. It should not have impact on each other. And then durability. Once a transaction has been committed, it will remain so. Got it. There are many techniques to scale a relational database: master-slave replication, master-master replication, federation, sharding, denormalization, and SQL tuning. Master-slave replication: the master serves reads and writes, replicating writes to one or more slaves, which serve only reads. Slaves can also replicate to additional slaves in a tree-like fashion. If the master goes offline, the system can continue to operate in read-only mode until a slave is promoted to master or a new master is provisioned. Okay, client keeps reading from the client reads and writes from the master, and then it is replicated to a couple of slaves, and then from the client, only the exclusive read operations are taken care. And if master goes down, one of these slaves will be promoted as master or another master is selected. Disadvantages of master-slave replication: additional logic is needed to promote a slave to master. See the advantages. Okay. Disadvantages. See the disadvantages of replication. Additional logic is needed to promote a slave to master. See the disadvantages of replication for points related to both master slave and master master. Master master replication. So master itself is replicated into multiple instances, and then both reads, which supports both reads and writes. Both master serve for reads and writes and coordinate with each other on writes. If either master goes down, the system can continue to operate with both reads and writes. Disadvantages: you will need a load balancer, or you will need to make changes to your application logic to determine where to write. Most master-master systems are either loosely consistent, violating ACID, or have increased write latency due to synchronization. Basically, um, if we need to see the consistent view, uh, like whenever something is written to this particular application, and some other client is trying to read from here, so we should delay that read until the replication happened from this, right? Or else it will see, or else this client would see an inconsistent view, because this is already updated some record and this still be using some other version of it, or the older version of it. So yeah, so those are the disadvantages. Let's see. Disadvantages of master-master application: you will need a load balancer, and or you will need to make change the application logic to determine where to write. Most master-master are either loosely consistent, okay, or have increased latency due to synchronization. Conflict resolution comes more into play as more write nodes are added and as latency increases. See the disadvantages of replication for points related to both master slave and master master. Disadvantages of replication: there is a potential for a loss of data if the master fails before any newly written data can be replicated to other nodes. Okay, that's a risk. So let's say in this architecture as well, whenever some write happens to this master, before it gets replicated to other nodes, if this master fails, then there could be a loss of data. It's the same with this master slave architecture as well as master master architecture as well. So that is one of the disadvantage. Writes are replayed to read replicas. If there are a lot of writes, the read replicas can get bogged down with replaying writes, and can't do as many reads. Okay, so the write transactions can, or the write replication can overwhelm the read replicas rather than allowing for the customers, allowing for the reads from the clients. It will be busy just replicating the latest updates. The more read slaves, the more you will have to replicate, which leads to greater replication lag. Okay, so that greater replication lag means once the write happens, all the clients would not be able to see the consistent version until it is replicated to all the slaves. So if it should be used only knowing that, okay, there would be a delay replicating to all the clients. On some systems, writing the master can spawn multiple threads to write in parallel, where read replicas only support writing sequentially with a single thread. Okay, replication adds more hardware and additional complexity. Okay, these things are kind of obvious, master master and master slave, but it gives a good pointers to talk about, like or articulate our thought process in a better way during the system design interviews. Let's get to the federation. I'm not sure if I have looked into this one. So there is something called as forums DB, users DB, and products DB. So let's see. Federation or functional partitioning splits up the databases by function. For example, instead of a single monolithic database, you could have 3 databases: forums, users, and products, resulting in less reads and writes, read and write traffic to each database, and therefore less replication lag. Smaller databases results in more data that can fit in memory, which in turn results in more cache hits due to improved cache locality. With no single central master serializing writes, you can write in parallel, increasing the throughput as well. Disadvantages of federation: federation is not effective if your schema requires huge functions or tables. you will need to update your application logic to determine which database to read and write. Joining data from two databases is more complex with a server link. Federation adds more hardware and additional complexity. Okay, scaling up to your first 10 million users. This could be an interesting watch, I guess. Let's see. We can save these things for later. Otherwise, we will uh, end up in a rabbit hole of the links. First, let's complete few of the things and then let's go. Scaling up to first 10 million users. Okay. So yeah, this is neat. So what they are basically telling is, rather than creating a single data base for an application, we can create multiple databases. So that would create smaller data required and then smaller replication lag as well between the master slave. And then also here they are saying with no single central master serializing writes, you can write in parallel, increasing the throughput as well. And the disadvantages are federation is not effective if schema requires huge functions or tables. And also we need to update the application logic to determine which database to write to or read from. And joining the data from multiple across the databases should be a headache. And federation adds more hardware and additional complexity since we are using multiple databases, so we would need more hardware for managing the same amount of data. So let's get to sharding. Sharding is this is the application and the load balancer, and then the same table is divided into multiple partitions here. Sharding distributes data across different databases such that each database can only manage a subset of the data. Taking a user's database as an example, as the number of users increases, more shards are added to the cluster. Okay. Similar to advantages of federation, sharding results in less reads and write traffic, less replication, and more cache hits. Index size is also reduced, which generally improves the performance with faster queries. If one shard goes down, the other shards are still operational, although you will want to add some form of replication to avoid data loss. Like federation, there is no single central master serializing writes, allowing you to write in parallel with increased throughput. Okay, let's see this one again. Similar to the disadvantage of federation, sharding results in less read and write traffic, less replication, and more cache hits. Okay. Index size is also reduced, which generally improves performance with faster queries. So if like the table size is reduced because we have divided it into multiple databases. So obviously the index size also would reduce, and that would result in improve the performance and results in faster queries. If one shard goes down, the other shards are still operational, although you will want to add some form of replication to avoid data loss. So in the individual databases, we should have some form of replication to avoid data loss. But the thing is, each shards work independently. If one of them goes down, it doesn't mean that the others are not operational. Others will continue to work. Like federation, there's no single central master serializing writes, allowing you to write in parallel with increased throughput. Okay, like federation, there is no single central master writing. Okay, so there's no single central master here. So central master based on the functionality in the federation. Here for a single functionality, we have been writing to, we have the separate databases defined. So each of them should have masters and slaves if we need to replicate that data, but there's no single master replicating to all of these shards. So that would allow us to write in parallel across the databases or across the shards. Common ways to shard a table of users is either through the user's last name initial or the user's geographical location. So this would be application specific, and based on that we will make the decision. You will need to update your application logic to work with shards. which could result in complex SQL queries. Data distribution can become lopsided in a shard. For example, a set of power users on a shard could result in increased load to that shard compared to the others one. So if we are not sharding, or if we haven't opted for a sharding strategy for even distribution, then it can create a bias. Like basically, if there is a power user in one of the shards, then most of the traffic and the data would go to that particular shard, whereas the other databases or the other partitions would remain free, relatively free. So that's the risk that they are quoting here. Data distribution can become lopsided in a shard. For example, a set of power users on a shard could result in increased load to the shard compared to the others. Rebalancing adds additional complexity. A sharding function based on consistent hashing can reduce the amount of transferred data. What is consistent hashing? We can look into that later. Joining data from multiple shards is more complex. That's almost close to impossible, or that's not advised or recommended. Sharding adds more hardware and additional complexity. That's obvious. We are splitting the data into multiple databases, so we will have a room for additional data or additional space in each of those, so that buffer and everything will cost more hardware. Sharding adds, okay, that's done. Sources for further reading: the coming of the shared database architecture and consistent hashing. So consistent hashing we will read about. That seems like a good read for us in the future, but okay. But before that, there are more important things according to me here. Let's cover those things. I captured the consistent hashing here. So let's go back here. Let's read about denormalization. Denormalization attempts to improve read performance at the expense of some write performance. Okay, that's a good point. Attempts to improve the read performance at the expense of some write performance. Redundant copies of the data are written in multiple tables to avoid expensive joins. Okay. Okay, redundant copies of the data are written in multiple tables to avoid expensive joins. Some RDBMS such as PostgreSQL and Oracle support materialized views, which handle the work of storing redundant information and keeping redundant copies consistent. Okay, it supports out of the box to keep the redundant copies consistent. Once data becomes distributed with techniques such as federation and sharding, managing joins across the data centers further increases complexity. Denormalization might circumvent the need for such complex joins. In most systems, read can heavily outnumber writes, 100:1 or even 1000:1. A read resulting in a complex database join can be very expensive, spending a significant amount of time on disk operations. That's true. I think these are self-explanatory. I don't have to comment on any of those. Disadvantage or denormalization. Data is duplicated. Constraints can help redundant copies of information stay in sync, which increases complexity of the database design. A denormalized database under heavy write load might perform worse than its normalized counterpart. Okay, all those things are true. SQL tuning. SQL tuning is a broad topic, and many books have been written as reference. It's important to benchmark and profile to stimulate and uncover bottlenecks. Benchmark stimulate high load situations with tools such as, what is this, AB? Okay, Apache HTTP server benchmarking tool. Okay, and then profile enable tools such as slow query log to help track the performance issues. Okay, these are certain things like slow query log. Okay, this can be used for profiling the database in order to understand the performance issues, and this benchmarking tool, which is AB, which is used to simulate the high load situations, and then yeah, it's just a high load simulation tool in order to help with benchmarking. Benchmarking and profiling might point you to the following optimizations. Tighten up the schema. MySQL dumps to disk in contiguous blocks for fast access. Use char instead of where for fixed length fields. Char effectively allows for fast random access, whereas with where you must find the end of the string before moving on to the next one. Wow, these are good suggestions I have not looked into. Use text for I do not even know if in the current company they are using char or where. Need to check. Use text for the large blocks of text such as blog posts. Text also allows for Boolean searches. Using a text field results in storing a pointer on disk that is used to locate the text block. Use int for larger numbers up to 2 power 32 or 4 billion. Use decimal for concurrency to avoid floating point representation errors. Use decimal for currency to decimal for currency to avoid floating point representation errors. Okay, that's a good suggestion as well. Avoid storing large blobs. Store the location of where to get the object instead. So instead of storing large blobs in the database, we can store it in object store, and we can store the URL or the link for that in the database. Where char of 255 is the largest number of characters that can be counted in an 8-bit number. Okay, often maximizing the use of byte in some RDBMS. Set the not null constraint where applicable to improve search performances. And use good indices. Columns that you are querying, select group by, order by, join, could be faster with indices. Indices are usually represented as self-balancing B trees that keep data sorted and allow searches, sequential access, insertions, and deletions in arithmetic logarithmic time. So we had discussed about it when we were talking about the binary trees in one of the live streams. So yeah, this is cool actually to connect to that on the system design side. Columns that you are querying, select group by, order by, join could be faster with the indices. Indices are usually represented as self-balancing B tree, self-balancing binary tree. Let's assume it as. Let's not get into the details as of now. These will be covered in a database course. We can learn about it in some future sessions. That keeps data sorted. We know that in the trees or the self-balancing binary trees, or self-balancing B trees, that keeps the data sorted and allows for searches, sequential access, and insertions and deletions in logarithmic time. This we are aware of. And if it is balanced, then we can always expect all these operations in logarithmic time. Placing an index can keep the data in memory, requiring more space. Okay. Writes could also be slower in the index. Also needs to be updated. Also be slower since the index also needs to be updated. So this is obvious. Like when we are writing just to the database table, it means just updating the database. And if we have created an index, the same value has to be updated in the index as well. So the write will become relatively slower. So we should we should decide the trade-off, like whether to create indexes based on that or not. When loading large amounts of data, it might be faster to disable indices, load the data, then rebuild the indices. Okay. When loading large amounts of data, it might be faster to disable indices, load the data, then rebuild the indices. It's a good tip. Denormalize where performance demands it. Avoid expensive joins and denormalize it. So denormalize, as we read, keeping a redundant copies of the data across multiple tables in order to improve the read without using expensive joins. Partition tables, break up the table by putting hotspots in a separate table to help keep it in memory. Tune the query cache. In some cases, the query cache could lead to performance issues. Okay. NoSQL. Okay, it is another beast now. So I think since we are looking into this, let's look into the NoSQL as well, or we can come back to this later also, since we are using we have decided to use SQL databases in this one. We looked into SQL. Let me think. We can just glance through the NoSQL since we are not using it. NoSQL is a collection of data items represented in a key value store, document store, wide column store, or a graph database. Okay, data is denormalized, so data is like, since we do not think of joining across multiple tables here, data is denormalized, and joins are generally done in the application code. So joins are done in the application layer, not in the database queries level. Most NoSQL stores lack true ACID transactions and favor eventual consistency. Okay, so there's no transaction support out of the box in most of the NoSQL databases, and it supports eventual consistency. Base is often that those are the core differences in the SQL and NoSQL databases. One thing is it doesn't support joins or the relationships in the database level. All those things we need to handle on in the application level, and also it doesn't support transactions, and it favors for eventual consistency. Base is often used to describe the properties of the NoSQL database. In comparison with the CAP theorem, base chooses availability over consistency. Okay. Okay. Basically available. Base means basically available, soft state, eventual consistency. Okay. Um, Basically available, the system guarantees availability. Soft state, the state of the system may change over time even without input. Eventual consistency, the system will become consistent over a period of time given that the system doesn't receive input during that period. Got it. In addition to choosing between SQL and NoSQL, it is helpful to understand which type of NoSQL database best fits your use case. We'll review key value stores, document stores, wide column stores, and graph databases in the next section. Key value stores. A key value store generally allows for O of 1 reads and writes and is often backed by memory or solid state drives. Data stores can maintain keys in lexicographic order, allowing efficient retrieval of key ranges. Okay. Generally allows O of 1 reads and writes. Okay, that is impressive. And it is often backed by memory or solid or SSD. Data stores can maintain key in lexicographic order, allowing the efficient retrieval of key ranges. I think DynamoDB is one of these. Let's see. Key value stores can allow for storing of metadata with a value. Key value stores provide high performance and are often used for simple data models or for rapidly changing data, such as an in-memory cache layer. Since they offer only a limited set of operations, complexity is shifted to the application layer if additional operations are needed. A key value store is the basis for more complex systems such as document store. Okay, it's the basis for more complex systems such as document store and in some cases a graph database. Sources and further reading key value store. Key value database, disadvantage of Redis architecture, memcached architecture. Okay. And then the document store. Here comes the document store. Okay. Document store. Okay. MongoDB, CouchDB. Some document stores like MongoDB, CouchDB also provide SQL-like language to perform complex queries. DynamoDB supports both key values and documents. Okay. DynamoDB supports both key values and documents. MongoDB and CouchDB are the document stores. Okay, a document store is centered around document, XML, JSON, binary, etc., where a document stores all the information for a given object. Document stores provides APIs or a query language to query based on the internal structure of the document itself. Note, many key value stores includes features for working with the values metadata, blurring the lines between these two storage types. So yeah, a lot of there's overlap between key value stores and the document stores. Based on the underlying implementation, documents are organized by collections, tags, metadata, or directories. Although documents can be organized or grouped together, documents may have fields that are completely different from each other. Some document stores like MongoDB and CouchDB also provide SQL-like language to perform complex queries. DynamoDB supports both key values and documents. Document stores provides high flexibility and often are used for working with occasionally changing data. Okay, got it. Occasionally changing data, not rapidly changing data. Here in the key value store is the base for more complex systems such as document store. Okay, key value stores provide high performance and are often used for simple data models or for rapidly changing data such as in-memory cache layer. Okay, and wide column stores, super column family, row key, column family, and then columns. Okay, let's see what is this one. A wide column store's basic unit of data is column, name or value pair. Okay, city San Francisco, state California, street. Okay, abstraction nested type is column family, row key, columns, column key value, timestamp. Okay, this is super column family. Row key could be 1. Yeah, columns is a collection of column key. This could be the column key, and then value, column key and value, and then the timestamp. Okay, a wide column store's basic unit of data is a column, name, value pair. A column can be grouped in column families analogous to SQL table. Super column families further group column families. You can access each column independently with a row key, and columns with the same row key form a row. Okay, columns with the same row key would form a row. Okay. Okay, row key is the row key, and all of them would form a row, even though they have different column names. Okay, got it. Each value contains a timestamp for versioning and for conflict resolution. Makes sense? Google introduced Bigtable as the first wide column store, which influenced the open source HBase, often used in the Hadoop ecosystem, and Cassandra from Facebook. Stores such as Bigtable, HBase, and Cassandra maintain keys in lexicographic order, allowing efficient retrieval of the selection key ranges. Wide column store offer high availability and high scalabilities. They are often used for very large data sets. Got it. Graph database. In a graph database, each node is a record, and each arc is a relationship between two nodes. Okay, let's see how it is stored. So ID, name, okay, age, ID, name, and age. So these are the nodes, and then ID 103. What is this one? Label members. Okay, ID 102. Label is member since this one. And then I do not understand what is written over here. But yeah, these things are clear, node definitions. In a graph database, each node is a record and each arc is a relationship between two nodes. Each arc is a relationship between two nodes. Graph databases are optimized to represent complex relationships with many foreign keys or many-to-many relationships. Graph databases offer high performance for data models with complex relationships such as social network. They are relatively new and are yet to widely used and are yet not yet widely used. It might be more difficult to find development tools and resources. Many graphs can be accessed with REST APIs. That is cool. And Neo4j is one of the popular ones. There is FlockDB and graph database. There is further reading. Explanation of base terminology. Okay, let's dive deep into the graph database sometime later. SQL or NoSQL. This is the key thing that we need to decide on. So let's close this and this is an interesting read. Let me see later. Okay, so we are at the decisive point here. How to choose or on what parameters we should choose either to use a SQL database or a NoSQL database in a system design. So here they have given relational data model, highly structured table organization with rigidly defined data formats and record structure. Document data model, collection of complex documents with arbitrary nested data formats, varying record formats. So each of the individual records can have different formats and there is flexibility for the schema. But here in the relational database model, highly structured table organization with rigidly defined data formats and record structure. Reasons for SQL: structured data, strict schema; relational data, need for complex joins and support for transactions, clear pattern for scaling, more established developer community code tools, etc. Lookup by index are very fast. Okay, these are the reasons for SQL. Reasons for NoSQL: semi-structured data, dynamic or flexible schema, non-relational data, no need for complex joins, store many terabytes or petabytes of data. So this is one of the main reasons. Non-relational data, if there are no joins or any relationship between multiple tables, no need for complex joins. Yeah, that's obvious from this point. Dynamic and flexible schema makes sense. Very data intensive workload, and then very high throughput for IOPS. So sample data well suited for NoSQL, rapid ingest of clickstream and log data. Okay, leaderboard or scoring data, temporary data such as shopping cart, frequently accessed hot tables, metadata or lookup tables. Scaling up your, okay, the same thing, SQL or NoSQL. Okay, this was a good exercise, but let's come back to the same problem. So this is the problem when addressing the system design. It's easy to get uh, get sidetracked to some concepts here. So let's focus here at least until designing the core concepts. So now we had this, coming back to this problem, we had a high level design which is very generic, and from that we wanted to create the core components specific for this problem. So use cases: we could use relational database as a large hash table, mapping the generated URL to a file server or and path containing the paste file. Instead of managing a file server, we could use a managed object store such as Amazon S3 or NoSQL document store. An alternative to relational database acting as a large hash table, we could use a NoSQL key value store as well. We should discuss the trade-off between choosing those two. So that is what we did as of now. The following discussion uses the relational database approach. Okay, the client sends a create paste request to the web server. The client sends the create paste request to the web server running a reverse proxy. So what is the reverse proxy? Again, let's not get sidetracked. Let's focus on this one. Reverse proxy is something like that is an endpoint exposed to the outside world or the client, and then if we get a request to reverse proxy, that would identify the web server that the request should be forwarded to. So that's the functionality of the reverse proxy. So that would hide the direct identifier or direct IPs of those web server instances from the external world, and hence makes it much safer as well. So yeah, the web server forwards the, and that way another thing is like we do not have to follow the there are chances of DDoS or what do you call that, malicious users bombarding the request into a particular web server and trying to bring that down. So rather than handling all those scenarios in each of the servers, what's the best practice is to define all those rules within the proxy layer, and then proxy is only exposed to the outside customers or outside internet, and the rest of them are configured to be accessed within network only, and then proxy will direct the traffic to the responsible web server. Okay, the client sends a create paste request to the web server running as a reverse proxy. The web server forwards the request to the write API server. So here they have separated the services to a couple of servers: write API server and then the read API server, at least as of now. and then the reverse proxy directs the create paste request to the write API server. The write API server does the following: generates a unique URL, checks if the URL unique by looking at the SQL database for a duplicate. If the URL is not unique, it generates another URL. If we support a custom URL, we could use the user supplied also check for a duplicate again. Saves to the SQL database paste table. Okay, there is a paste table. It will save that to the SQL database. Save the paste data to the object store. Save the actual text in the object store, and then gets the link for that one and saves that URL in the paste database. Returns the URL. Clarify with your interviewer how much code you are expected to write. The paste table could have the following structure: short link, characters char7 not null. So just now they mentioned if we know the fixed length in the SQL database, then it's better to use char rather than using where char which is variable character. So that's they're implementing that here. Short link, we know how many characters it can be, char7 not null. Expiration length in minutes, int, and that's not null, that's mandatory too. Created at date time, not null. Paste path, variable character, 255 characters, varchar of 255, and it's not null as well. And primary key is the short link out of this, so that is defined. So this is the table, paste table. Setting the primary key to be based on the short link column creates an index that the table uses to enforce uniqueness. We will create an additional index on created at. Okay, we will create another additional index at created at to speed up lookups, lock time instead of scanning the entire table, and to keep the data in memory. Reading 1 MB sequentially from memory takes about 250 microseconds, while reading from SSD takes 4x, and from disk takes 80x longer. Okay, from memory takes 250 microseconds, and while okay, let's read this again. This can serve as an important information. Setting the primary key to be based on short link column creates an index that the data table uses to enforce uniqueness. Okay, that totally makes sense. We will create an additional index on created at to speed up lookups, lock time instead of scanning the entire table. Okay, and to keep the data in memory. Okay, create the indexes to keep the data in memory and to speed up the lookups. Reading 1 MB sequentially from memory takes 250 microseconds, while reading from SSD takes 4x of reading from memory, and from the disk takes 80x longer. Okay, so this is from in memory multiplied by 4x is the solid state drive, multiplied by 80x is the disk storage, is the read from the disk storage. To generate the unique URL, we could take the MD5 hash of the user's IP address and the timestamp. MD5 is widely used hashing function that produces a 128-bit hash value. MD5 is uniformly distributed. Alternatively, we could also take the MD5 hash of randomly generated data as well. And base62 encode the MD5 hash. Base62 encodes to which work well for URLs. Base62 encodes to which works well for URLs, eliminating the need for escaping special characters. There is only one hashed result for the original input, and base62 is deterministic, no randomness involved. Base64 is another popular encoding but provides issues for URLs because of the additional plus and slash characters. The following base62 pseudocode runs in O of k time, where k is the number of digits is equal to 7. Okay, take MD5 hash for the user's IP address plus timestamp. MD5 is widely used for hashing function that produces a 128-bit hash value. MD5 is uniformly distributed. Alternatively, we could take the MD5 hash of randomly generated data. So to generate the unique URL, we could either use this or we could use this one. Encode the base62, encode the MD5 hash. Okay, take the MD5 and then we can encode the MD5 hash by using the base62. Makes sense. There's only one hash result for the original input, and base62 is deterministic as well. No randomness involved. Basics, yeah. So base encode number base is equal to 62. Base we are passing, and the number we are passing here. Digits is equal to nothing. While number is greater than 0, remainder is equal to modulo of number comma base. Digits dot push remainder. Number is equal to divide number by base, and then digits is equal to digits dot reverse. So this is a base encode, and base is equal to 62. Where are we using it? Modulo number by 62. Okay. Take the first 7 characters of the output, which results in 64 power 7 possible values, and should be sufficient to handle our constraint of 360 million short links in 3 years. URL is equal to base encode of MD5 of. So first thing is IP address plus timestamp. We should convert it into MD5, or we should apply the MD5 hash on top of that, and then we should encode that resultant by using base62 encode. Okay, this is good. Okay, we will use a public REST APIs. We will use a public REST APIs call, okay, expiration length in minutes, and paste contents hello world, https pastebin.com. Okay, this is this thing, and response should be a short link. For internal communications, we could use remote procedure calls or RPCs. For external, we will use REST APIs, and for internal communications, we will use RPCs. Use case, user enters okay, this was the first use case that was handled here. First use case was user enters a block of text and gets a randomly generated link. So okay, they are handling it by use case by use case. So let's take this one. User enters the text and gets a randomly generated link. So what things are important here? First thing is choosing to go with the relational. For this particular use case, I don't think it matters if we select the SQL database or NoSQL one database. Store the metadata in the table and the actual text content in an object storage such as AWS S3 or some document storage. So that's over. And then they have given the table structure, that one, the table schema that we can mention here. This looks good. Short link char 7, which is not null. And after short link, what else we need? We need the expiration time created at paste path, and then define the primary key expiration, which is int and not null. Okay, expiration length in minutes, so that is int and not null. We don't have to be descriptive so much. And paste link, So paste link is something which we can store as varchar, and that is also not null. This is the link of the AWS S3 storage or wherever it is stored. And then other than paste link, we need created at, which is like a metadata, and timestamp, or I think it's called date time. That type is called date time, and that is not null. For primary key, we are defining short link as a unique identifier here. And then another thing is we can create an index based on created at, in order to support faster access for the recent uploaded paste links. And yeah, how do we store the data? That is another thing. So the data is stored using this algorithm. We use MD5 and apply. Okay, use MD5 hash on top of the user IP address and timestamp, and then encrypt it using the base 62. Or yes, this isn't the right word, and then apply base 62 on the result of this. Okay, so we can have that one here, URL equal to base encode of MD5 of IP address plus timestamp for the URL length, whatever the URL length that we would need. Okay, this makes sense. And then yeah, and then use REST APIs for the external customers or clients, or external access, and use RPC for internal RPC to access it from the internal services. Access from internal systems. One of them can be protobuf. Okay. So now the second use case, user enters a paste URL and views the contents. So this one can be use case. Second use case is, okay, user enters a paste URL and views the content. Okay, in this case, let's see. Let's have a brief read, and then we can wrap these use cases. and then we can move on to the scaling. Okay, here the next use case is user enters the paste URL and views the content. The client sends a get paste request to the web server, so that would be a get request to be precise. The web server forwards the request to the read API server. Here in this context, web server is the reverse proxy. So that would forward the request into read API server. The read API server does the following: checks the SQL database for the generated URL. If the URL is in SQL database, fetch the page contents from the object store, else return an error message for the user. Makes sense. So those things are kind of obvious. And then yeah, format of the REST API and format of the response. Response should be the page contents created at and then the expression length and the use cases and the okay, that's the next use case. So get API to the web server that would be forwarded to read API, which would respond the uh, with the content or returns error if it doesn't exist or if it's not a valid request. So that should take care of it, and I think I can just write the response format if there is a successful response. This was actually cool. Like, should have copied this. Okay, that's not giving the same effect. Okay, so let's see this one. So this use case is the next use case that can be handled in simple ways. And then the next use case is for internal communications. We could use RPCs. Again, the same thing. We can read about RPCs later. It was asked during one of the most recent interviews for me. That what is gRPC and what is RPC and uh, what's my experience in those using those frameworks. So yeah, let's come here. Next case is use case. User enters a page URL and views the contents. That is done, right? User enters a page URL and views the content. Here, yeah, this is done. And here next use case is use case service track the analytics for the pages. So service tracks the analytics for the pages. So it's kind of weird in some of the system design interviews. The user or the interviewer expects you to keep drawing something rather than using text. I'm comfortable with text as I'm doing here, but yeah, like if the interviewer expects you to write more and more component diagrams and explain it based on that component diagrams itself, means you can write all this schema and all this formula across within the component diagram uh, close to the related content there. So let's see, use cases, service tracks analytics for the pages. Since real-time analytics are not a requirement, we could simply map reduce the web server logs to generate hit counts. Clarify with your interviewer how much code you are expected to write. Okay, hit counts and a map reduce job. This is cool. Since the real-time analytics are not a requirement, we could simply map reduce the web server logs to generate hit counts. Okay, so we can query the log from the web server and yeah, we can generate the hit counts. Clarify with your interviewer how much code you are expected to write. Extract the generated URL from the log file. Extract URL. Okay. Return the year and month portions of the timestamp. Okay. And then mapper. In the mapper, pass each log line, extract the extract and transform the relevant lines, emit key value pairs of the form. It is month and year, and then the URL, and then the hit count. Month and URL, month and year, URL, and then the hit count, and then those things will be reduced here. So for 2016 URL 0, I have aggregated these two, 1 plus 1 2. For 2016 for URL 1, it's just 1. I'm summing those things in the reducer and emitting the result. Some values for each key, some values for each keys within that given time, and emit key value pairs of the form. So that I think that's a simple map reduce function that we can write, where we are trying to draw analytics for the hit counts of a particular URL within a given time frame, which is month and year in this case. So what we can do, we can just write it as, since the real-time analytics are not, most of the system design interviewers doesn't expect us to code in that round, but this could be a good knowledge or good refreshers if in other rounds. Like I think I have written, I've ended up writing MapReduce code in one or two interviews before, even though I'm not interviewing for the specific job there, specific job related to MapReduce functions. We could simply MapReduce the web server logs to generate hit counts. Okay, I think that's a good justification as well, since real-time analytics, since the real-time analytics is not a requirement, we can simply map reduce the web server logs to generate the hit counts. Okay, this makes sense. Let's go with this for now. And then the next use case is the core one. Use case is, the core feature of the application. Service deletes the expired page. So let's look into that as well, how they are handling it. Service deletes the expired page. Okay, to delete the expired page, we could just scan the SQL database for all the entries whose expiration timestamp are older than the current timestamp. All expired entries would then be deleted or marked as expired from the table. Okay, deletion can be handled in two ways. Either it can be soft deleted or hard delete. Basically, usually in the systems we do mark it as marked for deletion, or we usually make it as soft delete in order to have the support for analytics, unless there is some compliance which is forcing us to delete that particular record. So here, I think this is like a basic way of handling it. We can just query through. That might not be the most performant way. I was hoping there will be some more creative ways, but here just scan through the SQL databases for entries whose expiration timestamp is exceeded. Okay, scan. This is like the brute force solution for that one. Scan through the database for all entries that are expired, that have expired timestamp, and mark them as deleted, and don't make it available, and make it unavailable for the reads. Okay, so if it is marked for deletion, then it should not be available for the reads from the application. Next thing is step 4, scale the design. Let's see. What do we do in this step? What do we do? This is pretty easy to handle within the time. I guess if the time given for the system design round is 45 minutes or so. uh, I'm not sure if this is easy, or now, since I'm thinking in a structured way of handling the system design, so that makes it more easier for me. I think that's the one thing I wished. One is how I would communicate my thought process better, and how I would structure my um, system design to be able to handle all the requirements within the given time. So it's already I can already feel the difference with, like, before I handle one system design. So let's keep going then. Okay, scale the design. Identify the address bottlenecks given the constraints. Identify and address the bottlenecks given the constraints. Okay, so now you can see the detailed design, little bit more details, design with little bit more details, like client is calling the DNS, and then okay, uh, and then there is a CDN is hosted for the object store. Like, we do not have to query from the object store directly, but there is a CDN which is fronting those static assets. And then there is a load balancer in front of the web server, which was acting as a reverse proxy. And then that load balancer is forwarding it to the reverse proxy, and then that is routing the request to appropriate web servers, which is write API and read API in this case. And then for the read API, we have a memory cache, and then for the write API, we are directly writing it to the SQL store, and we are reading from the read replicas as well if the cache doesn't contain the record that the user is querying for. And then the object store as well. A read API is reading from the object store if it is being if the user is querying from here. And yeah, and then the write API is writing to the object store as well. And analytics is reading from both the object store and then the SQL analytics table. So SQL analytics uh, might be the version that we are handling using like as we saw here. Uh, we are running a map reduce job, and we are storing the click counts and things like that, and we have that analytics stored in this SQL analytics table, and that is being queried from in the analytics service or the dashboard or whatever the tool this one is. Okay, this is pretty cool. Now I don't want to just copy this and paste this here. I need this to be in my muscle memory in order to draw this comfortably within the given time, rather than having hard time to draw this in the interviews. Okay, so yeah, as this one is good, all the use cases are handled. Let's read the scaling part. Okay, there is nothing much written actually. Let's see whatever is written. Important, do not simply jump right into the final design from the initial design. Okay, do not just simply jump into that. State you would do this iteratively. State that you would do this iteratively. Benchmark first. Number one is benchmark or load test. Number two is profile for bottlenecks. Address the bottlenecks while evaluating alternatives and trade-offs. Four is repeat. You keep doing that. See, design a system that scales to millions of users on AWS as a simple. See this one as a simple on as a sample on how to iteratively scale the initial design. Uh, okay, let's see that one as well. Design the system. Design a system that scales to millions of users on AWS. We can see this as next problem. So it's a generic one. Design any system on AWS for millions of users. So before going into that, this is RPC. We can read about RPC also later. And this is about reverse proxy. Let's get back to that later. In the next section, let's read about RPCs and RPCs and reverse proxies once, and then in the next elaborate section, what is this one? This is caching. I don't think we have come across like any complex caching requirement as of now. So let's stall it for whenever we come across it. This one we can look into that. We can look into this design or some other problem next. Let's see. So let's complete this one first. Okay, look into this system, design a system that scales to millions of users on AWS as a sample on how to iteratively scale the initial design. It's important to discuss what bottlenecks you might encounter with the initial design and how you might address each of them. Yes, this is like we cannot just write a diagram which addresses everything. If that's the case, we can just keep this page open and we can just write it off. There's no right solution, right or wrong solution in the system design. It depends on how you will create an impression or how you will create the communication channel between the interviewer during the interview. So there should be a logical way of conversing about the system. Like what was your initial thought process about the system? This was just a basic one. And then why you are adding certain components into this system and what exact bottlenecks they are addressing and how that would improve your system in order to scale for the requirement that is given. So that's the conversation you should continuously having. That's where I mentioned to keep the system design much more interactive is the key. Sometimes some interviewers might not implicitly be interactive. Then also you need to keep probing and try to make it as interactive as possible and extract as much of information as possible for requirements, and also you need to make sure that you are stating your assumptions and making the informed or the data backed decisions whenever you are adding a new component or um, deleting any components from the design or anything like such. Okay, here this is a good advice, but yeah, there's nothing about these components that are added. It's important to discuss what bottlenecks you might encounter with the initial design and how we might address each of them. For example, what issues are addressed by adding a load balancer with multiple web servers and adding a CDN, adding a master slave replicas. What are the alternatives and trade-offs for each? We will introduce some components to complete the design and to address the scalability issues. Internal load balancers are not shown to reduce clutter. Internal load balancers are not shown to reduce clutter. To avoid repeating discussions, refer to the following system design topics for main talking points, trade-offs, and alternatives. Okay, so here in this layer, like in this one, they have used DNS, they have used CDN, load balancer, horizontal scaling, web server, and API server. Okay, web server and API server. This is a reverse proxy and this is application layer. And then caching layer, RDBMS, SQL write master slave failover, master slave failover for SQL write, and master slave replication, okay, for read replicas as well, and consistency patterns and availability patterns. So I'm not sure about these things, consistency patterns and availability patterns. Okay, let's dive into this one. The analytics database could use a data warehousing solution such as Amazon Redshift or Google BigQuery, and an object store such as Amazon S3 can comfortably handle the constraint of 12.7 GB of the new content per month. Okay, to address the 40 average read replicas per second, higher at peak, 40 average read replicas per second. Traffic for popular content should be handled by the memory cache instead of database. The memory cache is also useful for handling the unevenly distributed traffic and traffic spikes. Okay, this makes sense. Since there is unevenly distributed traffic and traffic spikes, it makes sense to uh, keep those data in memory, like whichever is queried for such a long, for so many times, and then rest of the things we can query from the database. So the majority of the requests gets high performance since they since they query from the caching layer itself. The SQL read replicas should be able to handle the cache mess as long as the replicas are not bogged down with the replicating writes. Yeah, it won't be bogged down if we are using cache more often. So for average page writes per second with higher at peak should should be doable for a single SQL master slave. Otherwise, we will need to employ additional SQL scaling patterns like federation, sharding, denormalization, or SQL tuning. We should also consider moving some data to a NoSQL database. Okay. Asynchronism, microservices, message queues, task queues, back pressure, microservices. I think these things are not required for this design. External communication with clients, internal communications. Okay. The security sections, latency numbers, ongoing continue benchmarking and monitoring your system to address bottlenecks as they come up. Scaling is an alternative process, iterative process. Okay, so here let's see. An object store such as Amazon S3 can comfortably handle the constraint of 12.7 billion GB, 12.7 GB of the new content per month. So that should be fine. I'll just add that as a statement. The analytics database could uh, could use a analytics database could use a data warehousing solutions like Amazon Redshift or Google BigQuery. And to address these things, the memory cache is also useful for handling unevenly distributed traffics and spikes. This is an important criteria. Okay. And the SQL read replicas should be able to handle the cache misses. Okay. Okay, this is key point. And then 4 average pages per second should be doable for a single SQL write master slave. Otherwise, we'll need to see this one, but it should be doable for this particular system. Let's not overcomplicate it or over-engineer it if it's unless it's required. To avoid repeating discussions, refer to these things. Okay, we will introduce some components to complete the design and to address the scalability issues. Internal load balancers are not shown to reduce clutter. Okay, internal load balancers are not shown. Like in front of these particular write API and read API also, there are, since there is a workload, I mean, there are a number of workloads for these servers, there will be a load balancer sending the traffic to the appropriate instance um, rather than a web server choosing. So that is not being shown. To keep it simple, nowadays it's kind of obvious. If we are writing a web server with multiple instances, it will be a distributed server, and we will have a type of load balancer distributing the load across those instances. To address the 40 average read replicas per second traffic, okay, memory cache, in memory cache, these things were done. Do not simply jump onto, okay, state iteratively, benchmark, load tests, profile, okay, address the bottlenecks, trade off, repeat. It's important to discuss what bottlenecks, okay, these are like the breaches, CDN, okay, CDN and master slave. Here, we know why DNS is used, why CDN is used, why this load balancer came to picture, and why this memory cache, we have already addressed it here. We have commented about the analytics, SQL analytics database, and okay, we haven't spoken about CDN. That seems like an important thing. CDN provides caching for the static asset, so we can use it and the clients can query the, or client can access them frequently accessed static file or static file content from the CDN directory, which resides close to the client location, client's geographical location. Okay, so that's one thing. So let's read about CDN. That is in this one, I think this is the major improvement compared to before. Load balancer is a significant thing that we can talk about, and then this caching layer is a significant difference that could make a significant difference that we can talk about. during the interview. So I think we already looked into, no, we haven't looked into load balancer or CDN or this thing. So let's look into that one since they are related to this particular exercise. And then reverse proxy also we can just take a look, and then cache. So let's load balancer, CDN, reverse proxy, and cache. Okay, and before doing that, let's complete this system design here. I will just copy it from the next design onwards. I'll try to use a whiteboard to draw the design by myself. But here I'm just being lazy. Okay, what is happening? Why am I not able to paste this? Copy image and paste the image. Okay. Okay, let's leave it as it is. So here the key thing is object store. Here the analytics database, Redshift, okay. Memory cache, okay, those are already in block, in the bold letters, and CDN should be bold. So these concepts are the pieces. Let's address these in the next section, all these pieces that we want to talk about. Let's take a break before that and see how's it going. I'll be back in 5 minutes. Okay, let's get back to our learning now. So yeah, rather than diving directly into this one, let's look into the other components. So we noticed in the previous design, we can mark this as complete for now, but we needed to collect more information about how the DNS improve, how adding this component, not DNS specifically, we don't have to explain it. It's self-explanatory. How CDN improved the performance here, adding CDN in front of the object store, and how adding a load balancer here in front of the web server, and how adding a cache layer or in-memory cache layer in front of the read replicas improved the performance. So let's look into that in detail. I think each of the engineers who are trying to read or prepare for system design interviews, we all know how the memory cache and how the load balancers and CDNs work. But I think it's what we are doing here is the exercise in order to explain it convincingly in the system design interviews, and logically explaining why it is needed for a particular design component. So let's see. So first, we are starting with load balancer. So here, pick a worker to forward the request. So there is a client and there is a dispatcher, and there are multiple workers backed by databases. So this is a rough diagram that they have, or a common diagram that we come across in each of the systems. What they are doing: pick a worker to forward request, random, round robin, least busy, sticky session, or cookies by request parameters. Okay, these are the different strategies that we can choose a worker from. Wait for its response and wait for its response and forward the response to the client. So pick a worker to handle a request and then wait for the response to be returned from that worker and then forward that request back to the client. Load balancers distribute incoming client requests to computing resources such as application servers and databases. In each case, the load balancer returns the response from the computing resource to the appropriate client. Load balancers are effective at preventing requests from going to unhealthy servers. Okay, so this is one of the big advantages. We don't have to handle those things manually. If we put a load balancer and if we configure a health check, which keeps pinging every worker that is assigned behind it at a scheduled interval, and if it notices one of the worker is unhealthy, then it will make sure that the requests are not forwarded to that particular worker and prevents overloading the resources. And also, yeah, it will try to distribute the load across the servers or the workers rather than overwhelming one of those, helping to eliminate a single point of failure. Okay, so that makes sense as well. So helping to eliminate the single point of failure, because if we have only one worker instance and if that is failing to serve the request, then there are other ones which can serve the request efficiently, so it will help eliminating the single point of failure. Load balancers can be implemented with hardware, expensive, or with software such as HA proxy. Additional benefits include SSL termination, decrypt incoming requests, and encrypt the server response, so backend servers do not have to perform these potentially expensive operations. Removes the need to install the certificates on each server. Session persistent issue cookies and router traffic clients route specific clients request to same instance if the web apps do not keep track of the sessions. To keep to protect against failures, it's common to set up multiple load balancers either in active passive or active active mode. Load balancers can route traffic based on various metrics, including random, least loaded, session or cookies, round robin or weighted round robin, and layer 4 and layer 7. Okay, let's see layer 4 load balancing. Layer 4 this always confuses me. Layer 4, layer 7, these terminologies about networking. Let's read about it. Layer 4 load balancing. Layer 4 load balancers look at info at transport layer to decide how to distribute the request. Generally, this involves the source, destination IP address, and ports in the header, but not the contents of the packet. Layer 4 load balancers forward the network packets to and from the upstream server, performing network address translation or NAT. Layer 7 load balancing. Layer 7 load balancers look look at the application layer to decide how to distribute the request. So layer 4 load balancers look at the transport layer, and layer 7 load balancers look at the application layer. At some point of time, let's dive deep into these ones as well. So here in the load 7 layer 7 load balancing, it looks into the application layer to distribute the request. This can involve contents of the header and message and cookies. It will just look into the contents of the header, message, and cookies. But in the transport layer, it was looking into source and the destination IP address and the ports. Okay, here the header, message, and the cookies. Layer 7 load. So layer 7 is more close to the application. Layer 4 is still in the transport layer, and it is just looking into the source and the destination IP addresses. Okay, here load balancers terminate network traffic, reads the message, make a load balancing decision, then opens a connection to the selected server. For example, a layer 7 load balancer can direct video traffic to servers that host videos while directing more sensitive user billing traffic to security hardened servers. Okay, that can be customized based on the underlying servers. At the cost of flexibility, layer 4 load balancing requires less time and computing resources than layer 7. Layer 7 is more can be more customized and specific to the use cases. Although the performance impact can be minimal on modern commodity hardware. Horizontal scaling. Load balancers can also help with the horizontal scaling, improving the performance and availability. Scaling out using commodity machines is more cost efficient and results in higher availability than scaling up a single server on more expensive hardware called vertical scaling. It is also easier to hire for talent working on commodity hardware than it is for specialized enterprise systems. Okay, that makes sense. Vertical scaling means to say buying more expensive hardware, or like for example, if we are considering one machine, having a machine with more memory and more um, and more disk space and everything. Whereas a commodity hardware means like having several decent machines which can support the traffic and distributing the load across all those commodity hardware. That seems like an easier one, and it results in more availability. That's what they are telling here. That improves the performance and availability both. Disadvantages of horizontal scaling. Scaling horizontally introduces complexity and involves cloning servers. Servers should be stateless. In this case, servers should be stateless. So usually most of the states are stored in the database, or we will have a intermediate caching layer. So most of the server design would work with this pattern. They should not contain any user related data like sessions or profile pictures or anything. Sessions can be stored in a centralized data store such as database, SQL or NoSQL, or a persistent cache like Redis or Memcached. Downstream servers such as caches and database needs to handle more simultaneous connections as upstream servers scale out. Okay. Disadvantages of the load balancer. The load balancer can become a performance bottleneck if it does not have enough resources, or if it's not configured properly. Makes sense. Introduce a load balancer to help eliminate a single point of failure result in increased complexity. A single load balancer in a single point of failure configured multiple load balancers further increases complexity. Okay, let's read about it again. The load balancer can become a performance bottleneck if it does not have enough resources, or if it is not configured properly. Basically it adds one more latency, like rather than us hitting the uh, machines or the servers directly, we have introduced another layer here, the load balancer, which will read the request and then forwards it to the corresponding servers. So that would definitely add latency, and it will be a performance bottleneck. Like let's say if there is a single machine behind the load balancer, then it does not make sense. Load balancer is not adding any advantage. So in those cases, we don't need it. But in the cases when we have to route the traffic or distribute the traffic between multiple web servers, like there are hundreds of machines or instances that can be backing a particular service. in order to distribute the load in those scenarios, we need a load balancer. And then here, introducing a load balancer to help eliminate a single point of failure result in increased complexity. Okay. A single load balancer is a single point of failure. So now, now obviously, like this could be a single point of failure. That's why we have multiple instances and have done a horizontal scaling here. But again, what if there is a single instance of load balancer and if that failed? So that's what they are talking about here. That's a good problem. That's a good point there. A single load balancer is a single point of failure. So there are strategies to overcome that. Configuring multiple load balancers further increases the complexity. So that is the disadvantage. So there is Nginx architecture. This is um, one of the popular options for using proxy. And okay, scalability layer 4, load balancing layer 7, ELB listener, yeah, elastic load balancer listener config. Let's look into Nginx architecture, not now, sometime later, or I can just keep it as uh, as a resource for my further reading. So I hope I'll get back to these things, but not very time soon. I need to read more system designs. After that, I can make time for this ones. Now, Nginx. Yeah. So yeah, this is done. We can close the load balancer for now. Okay, CDNs. CDNs are an important piece as well. For CDN, as soon as we talk about a CDN, I remember either AWS CloudFront or Cloudflare. These are few of the offerings for the CDN network. So a content delivery network is a globally distributed network of proxy servers. Okay, you can see here. Yeah, globally distributed network of proxy servers serving content from locations closer to the user. This is the key point. Serving content from locations closer to the user. Generally, static files such as HTML, CSS, or JavaScript, and photos and videos are served from CDN. Okay, sorry, there was a disturbance, so let me read it out again. A content delivery network is a globally distributed network of proxy servers serving content from locations that is closer to the user. Generally, static files such as HTML, CSS, and JavaScript or photos and videos are served from a CDN. Although some CDNs such as Amazon's CloudFront support dynamic content as well, the site's DNS resolution will tell clients which server to contact. Okay, the site's DNS resolution will tell the clients which server to contact. Serving content from CDNs can significantly improve performance in two ways. Users receive content from the data centers close to them. Okay. And then your servers do not have to serve requests that the CDN fulfills. Okay, we can directly call the CDN instead of going via the servers. Push CDNs. Push CDNs receive new content whenever changes occurs on your server. You take full responsibility for providing content, uploading directly to the CDN and rewriting URLs to point to the CDN. You can configure when content expires and when it is updated. Content is uploaded only when it is new or changed, minimizing traffic but maximizing storage. Sites with small amount of traffic or sites with content that isn't often updated work well with push CDNs. Content is placed on the CDNs once instead of being re-pulled at regular intervals. Okay, pull CDNs. Okay, let's look into push CDNs again. It did not make sense to me. Push CDNs receives new content whenever changes occur on your server. Okay, you take full responsibility for providing content, uploading directly to the CDN, and rewriting URLs to the rewriting URLs to point to the CDN. You can configure when content expires and when it is updated. Content is uploaded only when it is new or changed, minimizing traffic but maximizing storage. Sites with small amount of traffic or sites with content that isn't often updated work well with the push CDNs. Okay, since it is not updated. Content is placed on the CDNs once instead of being re-pulled at regular intervals. Okay, this is the push CDN architecture. So our application server has to push the content into CDN explicitly. Pull CDNs grabs new content from your server when the first user requests the content. So whenever the first user makes a request to something like a CloudFront distribution or a Cloudflare, then it will check if that content is available locally in that CDN. If not, it will make a query to the backend server and then gets that content, and then it will cache it there for the request. Okay. So pull CDNs grab the new content from your server. Pull CDN. Okay, it pulls on the first request on the from your server. When the first user requests the content, you leave the content on your server and rewrite URLs to point to the CDN. Okay, you leave the content on your server and rewrite URLs to point to the CDN. This results in a slower request until the content is cached on the CDN. This results in a slower request until the content is cached on the CDN. A time to live determines how long the content is cached. Pull CDNs minimizes storage space on the CDN, but can create redundant traffic if files expire and are pulled before they have actually changed. Okay. Sites with heavy traffic work work well with pull CDNs, as traffic is paired out of more evenly with only recently requested content remaining on the CDN. Makes sense. It is like a cache basically, but not sitting near the server, but it is sitting in a completely different geographic location close to the user, and a user can query from there. For example, it doesn't make sense to like, let's say if a news or if a trend or a meme or a video is going viral in a particular geographic location, let's say if it is going viral somewhere in Asia, and if other content are going viral somewhere in the West here, so it doesn't make sense to cache the viral videos of Asian or the Asian viral videos in the CDN or the location in the West, and vice versa. So more people or the more users are querying for that video on that particular geographical location. So if we cache that content in that particular CDN, then it can help improve the performance in a drastic way, and also it can work as an efficient way of using the CDN storage as well. Okay, disadvantages. Let's look into that. CDN costs could be significant depending on traffic, although this should be weighed with additional costs you would incur not using a CDN as well. Content might be stale if it is not updated before the TTL expires it. CDNs requires changing the URL for static content to point to the CDN. Okay. Globally distributed content delivery, the differences between the push and pull CDNs and Wikipedia. Okay. I think this much of information is good enough for system design interviews. Let's look into the other things when we are like looking to learn about CDN exclusively. Let's move on to the next topic now. Reverse proxy or the web server. A reverse proxy is a web server that centralizes internal services, provides unified interface to the public. I think I already spoke briefly about it. So reverse proxy is like it will hide or abstract away all the details of our internal web servers from the public facing internet. So yeah, that's what is mentioned, the key thing. A reverse proxy is a web server that centralizes internal services and provides unified interfaces to the public. Requests from the clients are forwarded to a server that can fulfill it before the reverse proxy returns the server's response to the client. Okay, makes sense. Additional benefits include increased security. We spoke about it. Hide information about backend servers, blacklist IPs, limit number of connections per client. So we can define all the rules in a central place rather than defining all those rules across all the servers within the network. Increase scalability and flexibility. Clients only see the reverse proxy's IP, allowing you to scale servers or change their configuration. SSL termination, decrypt incoming requests and encrypt the server responses so backend servers do not have to perform these potentially expensive operations. Okay, decrypt the incoming request and encrypt the server responses so the backend servers do not have to perform those potentially expensive operations. Removes the need to install these certificates on each servers. Compression compress the server responses. Caching returns the response from the cached request, response for the cached request. Static content serve the static content directly, HTML, CSS, JavaScript, photos, videos, etc. Load balancer versus reverse proxy. Okay, this is a good read. Deploying a load balancer is useful when you have multiple servers. Often load balancers route traffic to a set of servers serving the same function. Reverse proxies can be useful even with just one web server or application server, opening up the benefits described in the previous section. Solutions such as Nginx and HA proxy can support both layer 7 reverse proxying support both layer 7 reverse proxying and load balancing. Layer 7, as we saw in the load balancing, it is application layer. So application layer reverse proxying and load balancing. Okay, what's the difference? In load balancing is mostly used when there are multiple servers are involved, but reverse proxy can provide you the benefit even when there is a single instance behind it, because it provides the security and it will abstract away the details of that of where the server is running or which IP and all that from the external internet. um, yeah, and then deploying the load balancer is useful when often load balancers route the traffic to a set of servers, supplying this serving the same function. Okay, reverse proxies can be useful even when with just one server or the application layer, opening up the benefits described in the previous sections. Solutions such as Nginx. Okay, in one of my experiences, we have used reverse proxy when we wanted to, um, like from a single platform service, if we want to route the request to individual services which handle that specialized request. For example, if there is a AWS console, there are like hundreds of pages in AWS console. There is a EC2 page, S3, and maybe some separate things for DynamoDB and everything. So if we want to route the request from that is coming from the internet or the external world, that can be processed by a reverse proxy, and then once it is processed, that can route the request to the individual applications which is handling the request for the respective consoles, like an S3 console or a EC2 console or things like that. Yeah, that could be a good use case. Introducing the reverse proxy results in increased complexity. Okay, a single reverse proxy is a single point of failure. Configuring multiple reverse proxies, that is failover, further increases the complexity. Yeah, this is the same problem that we saw in the load balancing. A single one would pose it as a single point of failure, but having configuring the multiple reverse proxies, I think it should be like any other web servers. Hiding the details of the web servers behind it or multiple web servers behind it. So there should be redundancy configured for this ones as well. Reverse proxy versus load balancers, Nginx architecture, and all these things. Okay, so that is done. There is an interesting diagram here. Request goes through the load balancer, and there are multiple web servers, and there are multiple platform servers, which is fronted or which is backed by the databases. Separating the web layer from the application layer allows you to scale and configure both layers independently. Adding a new API results in adding application servers without necessarily adding additional web servers. Okay. The single responsibility principles advocates for small and autonomous services that work together. Small teams with small services can plan more aggressively for app growth. Workers in the application layer also help enable asynchronism. Okay, these are like opinionated concepts, and there's no right solutions for these things. How we should go about the design. I have seen at multiple places going about designing it in multiple different ways. Microservices, we should read about microservices for sure. Microservices, service discovery, and all that. But now it might not be the right time. It is vast. We need to understand console, HCD, Zookeeper, and all that. We'll look into it at some point. Let's see how. Let's copy this link and let's keep it for our pending list. So not from this material alone, I think for microservices, there are so many good materials available, so many good books that where we can read it from. So let's do that at some point. Okay, so now we are done with the reverse proxy. So what's next? And this is cache. Okay, this is one of the important things. So client is calling the dispatcher. What dispatch is doing? It is looking up at the cache. If it finds the result, then return to the client. Otherwise, forwards to the worker, store results to the cache. Okay. Otherwise, it is if the result is not found, then it is forwarding it to the specific worker to handle that request. And whatever the result comes out of that worker, it is storing and updating the cache and then responding to the client. Caching improves page load times and can reduce the load on servers and databases. In this model, the dispatcher will first look up if the request has been made before and try to find the previous result to return in order to save the actual execution. Databases often benefit from a uniform distribution of reads and writes across its partitions. Popular items can skew the distribution, causing bottlenecks. Putting a cache in front of the database can help absorb uneven loads and spikes in traffic. Okay, that makes sense. Caching improves page load times and can reduce the load on the servers and databases. Okay, uh, in this model, uh, the dispatcher will first look up the if the request has been made before and try to find if the previous result to return in order to save the actual execution time. Database often benefit from uniform distribution of reads and writes across its partitions. Okay, popular items can skew the distribution, causing the bottlenecks. Uh, yeah, so putting a cache in front of the database can help absorbing uneven loads and spikes in traffic. All those things are self-explanatory and important key things. Client caching. Caches can locate on the client side, OS or browser, or server side, or in a different caching layer. CDN caching, we just spoke about it. CDNs are considered a type of cache. Web server caching. Reverse proxies and caches such as Varnish. Okay, I haven't heard of it. Varnish can serve static and dynamic content directly. Web servers can also cache requests, returning response without having a contact application servers. Database caching. Your database usually includes some level of caching in a default configuration optimized for generic use case. Tweaking these settings for specific usage patterns can further boost the performances. Okay, this is good. Application caching. In-memory caches such as memcached and Redis or key value stores between your application and your data storage. Okay, between the application and data storage, because that's the most expensive operation if we have to read from the disk. So if we can avoid it by reading from an in-memory data store, that is golden. That would increase the performance in several folds. Since the data is held in RAM, it is much faster than typical databases where data is stored on disk. RAM is more limited than disk. RAM is more limited than disk, so cache eviction algorithms such as LRU or least recently used can help invalidate cold entries and keep hot data in RAM. So yeah, why we keep data in databases instead of memory? Because keeping everything in memory is going to be expensive, and disk storage is relatively cheap. But so now what do we do? How to optimize it? So the most frequently used records or the data should be used in the cache layer or in memory, and then we can keep the rest of the things in the disk, and then whenever we require we can directly query the database for that. So now the same thing is explained as cold entries and or hot entries in hot data here. Redis has the following additional features. Persistence option. Redis is a cache, but it has the persistence option as well. Built-in data structures such as sorted sets and lists. Okay, it has its own built-in data structures also, like sorted sets and lists. There are multiple levels you can cache. There are multiple levels you can cache that fall into a generic categories: database queries and objects, row level, query level, fully formed serializable objects, and fully rendered HTML. So all these can be cached. There are multiple levels you can cache that falls into general categories: database queries and objects. Database queries like row level, query level, and then fully formed serializable objects, fully rendered HTML. Generally, you should try to avoid file-based caching as it makes cloning and auto-scaling more difficult. Okay, cloning and auto-scaling more difficult. Caching at the database query level. Whenever you query the database, hash the query as a key, and store the result into the cache. This approach suffers from expiration issues. Hard to delete a cached result with complex queries. If one piece of data changes, such as table cell, you need to delete all the cached queries that might include the changed cell. Caching at the object level. See your data as an, okay, this one was also kind of self-explanatory. Caching at the database query level, they're asking to cache based on by creating a hash function of the query and making it as a key and storing it in the cache level. And the downside is basically if we just change one of the cell or one of the field when we are querying, then that we cannot query from the cache again. It will go back to the database to query, and then that will invalidate the cache, and we will have to re-update the cache. So here, caching at the object level, see your data as an object. See your data as an object, similar to what you do with your application code. Have your application assemble the data set from the database into a class instance or a data structure. Remove the cache object or remove the object from cache if its underlying data has changed. If its underlying data has been changed, then remove it from the cache. Allows for asynchronous processing. Workers assemble objects by consuming the latest cached object. Okay. Allows for asynchronous processing. Workers assemble objects by consuming the latest cached object. Okay. Suggestions of what to cache. User sessions should be cached. Fully rendered web pages should be cached. Activity streams and user graph data. Okay. When to update the cache. Since you can only store a limited amount of data in the cache, you will need to determine which cache update strategy works best for you. Cache aside. Okay, there is the cache aside here. Client, cache, and then storage. The application is responsible for reading and writing from storage. The cache does not interact with storage directly. The application does the following. So cache aside is a strategy. Basically, like we are talking about the cache update strategies here. Cache aside is one of the strategies. So here the client is querying from both the storage and the cache, and then takes the responsibility of updating the cache and everything. The application is responsible for reading and writing from storage. The cache does not interact with the storage directly. The application does the following: look up for entry in the cache resulting in a cache miss, load the entry from the database, add entry to the cache, and return the entry. Okay, so a code snippet for the same thing. Memcached is generally used in this manner. Subsequent reads of data added to the cache are fast. Cache aside is also referred to as a lazy loading. So yeah, lazy loading. That is kind of obvious. Only requested data is cached, which avoids filling up the cache with data that isn't requested. Disadvantages of cache aside: each cache miss results in 3 trips, which can cause a noticeable delay. Data can become stale if it is updated in the database, if it is updated in the database directly. Okay. This issue is mitigated by setting a time to live or TTL, which forces an update of the cache entry, or by using write through. When a node fails, it is replaced by a new empty node, increasing the latency. So all the cache would be gone when the node failed. Okay. So write to cache. Okay, this is the next one. Write through cache. Write through cache is there it was a write aside, I guess, or cache aside. It was a cache aside, and then it is write through cache. Write through cache is user is interacting with the cache, and cache is interacting with the database directly. Like, let's see, the application uses the cache as the main data store, reading and writing data to it. So application uses cache itself as the main data store. It reads and writes from the writes data from and to the cache. While the cache is responsible for reading and writing to the database, cache is responsible for the rest of the things. Application adds or updates entry in the cache. Okay, here, and then cache asynchronously writes entry to the data store. Okay, and then we return. Application code set user. Okay, if we just do this cache code, there will be a cache code as well, which should update the database, and then cache, and then set it in the cache layer as well. Write through is a slow overall operation due to the write operation, but subsequent reads of just written data are fast. Okay, so in the write through cache, write operations are slower as expected, but the subsequent reads are fast. Users are generally more tolerant of latency when updating data than reading the data. Data in cache is not stale. Data in cache is fresh every time whenever we update the database, the cache gets updated as well. When a new node is created due to a failure or scaling, the new node will not cache entries until the entry is updated in the database. Cache aside in conjunction with write through can mitigate this issue. Okay, when a new node is created during failure or scaling, the new node will not cache the entries until the entry is updated in the database. Cache aside is in conjunction with write through. Okay, cache aside in conjunction with write through can mitigate this issue. Okay, so that means it will vary from the cache. If the record does not exist, then it has to look for the entry in the database and then see. And most of the data written never be read, which can be minimized with a TTL. Okay, they have provided a solution as well with the downside. And next thing is write behind or write back. So user is writing to the cache and then return to the user, add an event to the queue, and then there is an event processor which reads from the queue and updates the database asynchronously, not in the request path. So that would increase the performance basically. Whenever we want to write it to the database, it won't write immediately, but it will add it to a queue, and then there would be a job which will write it to a database. So that would increase the write latency, but it won't block the request or block the user on that operation. And then also the consistency will not the yeah consistency will not be there, but availability will be prioritized. Select and execute event asynchronously. In write behind, the application does the following: add or update entry in the cache, okay, and then asynchronously write entry to the data store, improving the write performance. Disadvantages of write behind: there could be data loss if the cache goes down prior to its content hitting the data store. Okay, it is more complex to implement write behind than it is to implement cache aside or write through because of a lot more components being added. That itself is an application. And then refresh ahead. There is a client and then a cache and then a storage. You can configure the cache to automatically refresh any recently accessed cache entry prior to its expiration. Refresh ahead can result in reduced latency versus read through if the cache can accurately predict which items are likely to be needed in the future. Disadvantages of refresh ahead: not accurately predicting which items are likely to be needed in the future can result in reduced performance than without refresh ahead. Disadvantages of the cache: need to maintain consistency between the caches and the source of the truth, such as database through cache invalidation. Cache invalidation is a difficult problem. There is additional complexity associated with when to update the cache. Need to make the application changes such as adding Redis or memcached. Okay, sources for further reading from cache to in-memory data grades, scalable system design patterns, introduction to architecting systems for scalability, availability, stability, and patterns. Availability, so many good resources are there. AWS Elastic Cache Strategies, Wikipedia. Scalable system design patterns. What is this? Scatter and gather result cache. Okay, I like this representations of the systems. I wonder which tool did they use. If someone knows, please comment. Varnish. Okay, what is Varnish? Varnish HTTP cache. This is Varnish cache, the high performance HTTP accelerator. Varnish is available in this one. Technical questions about Varnish would be okay. Circle CI test. Again, it will take me back here. Okay, just they have releases here. Get help, security and documentation. Okay, one is software. Accelerate delivery of content, apps, and data. One is industry leading caching solutions help you accelerate, secure, and scale HTTP delivery workflows from APIs and apps to AIML. Reach more people, grow your business, and keep costs under control with faster, more efficient digital infrastructure. Okay, that makes sense. It's out of scope for us for now. This one we can keep it aside. Reverse proxy we already looked into. RPCs we haven't, and then we haven't went through this. RPCs, let's see this concept. So client processes and server processes, there is a request, there's a reply, and then communication module here, client stub procedure, client program, and server stub procedure, dispatcher. Okay, let's see. In RPC, a client uh, causes procedure to execute on a different address space, usually a remote server. The procedure is coded as if it were a local procedure call, abstracting away the details of how to communicate with the server from the client program. Remote calls are usually slower and less reliable than local calls, so it is helpful to distinguish RPC calls from local calls. Popular RPC frameworks include Protobuf, Thrift, and Avro. So this is there is a gRPC. This is developed by Google, I guess. Thrift might be some open source solution by Meta. Yeah, Avro I haven't used it before. RPC is a request response protocol. Client program calls the client stub procedure. The parameters are pushed onto the stack like a local procedure call. It feels like a local procedure call, but it might not be the actual local procedure call. Client stub procedure marshals or packs procedure ID and arguments into a request message. Okay, packs the procedure ID and arguments into a request message, the client stub procedure. Client communication module, OS sends the message from client to the server. Okay, there is a message sent from client to the server. Server communication module, OS passes the incoming packets to the server stub procedure. So there is a communication module on the server side as well. So the packets are passed to that. Server stub procedure unmarshals the result, calls the server procedure, matching the procedure ID and passes the given arguments. The server response repeats the same step above. So the advantage as opposed to the REST API or things like that is um, the client and the server agreed onto a contract of how the message passing happens, and that would make up for efficient um, efficient communication between the client and the server. So instead of sending it in like in a big string or vast method, so here in this case it will save on like, okay, parameter 1, it will just send the ID of that parameter, and it will send the ID of the second parameter instead of sending it as a string like name or email address or things like that. So that makes it up for efficient communication, I mean efficient way for communication. Sample RPC calls. Okay, get some operation data ANID, post another operation. Okay, this one. RPC is focused on exposing behaviors. RPCs are often used for performance reasons with internal communications, as you can handcraft native calls to better fit your use cases. Choose a native library SDK when you know your target platform. You want to control how your logic is accessed. You want to control how error control happens off your library. Performance and end user experience is your primary concern. HTTP APIs following REST tend to be used more often for public APIs. Disadvantages of RPC: RPC clients become tightly coupled to the service implementation. A new API must be defined for every new operation or use case. It can be difficult to debug RPC. You might not be able to leverage the existing technologies out of the box. For example, it might require additional efforts to ensure RPC calls are properly cached on caching servers such as Squid. Representation REST. representation, state transfer, or REST. REST is an architectural style enforcing the client-server model where the client acts on a set of procedures, acts on a set of resources managed by the server. The server provides a representation of resources and actions that can either manipulate or get a new representation of the resources. All communication must be stateless and cacheable. These are the four qualities of RESTful interface. Identify resources, the URI in HTTP, change with representations, verbs in HTTP, use verbs, headers, and body, use the same URI regardless of any operation, self-descriptive error message, state responses in HTTP, use status code, don't reinvent the wheel. HTML interface for HTTP. Your web service should be fully accessible in a browser. Sample REST calls get some resources slash ID, put some resources, some ID. Okay, another data, another value. Okay, REST is focused on exposing the data. It minimizes the coupling between the client and server and is often used for public HTTP APIs. REST uses a more generic and uniform method of exposing resources through URIs, representation through headers, and actions through verbs such as get, post, put, delete, and patch. Being stateless, REST is a great REST is great for horizontal scaling and partitioning. Disadvantages of REST: with REST being focused on exposing data, it might not be a good fit if the resources are not naturally organized or accessed in a simple hierarchy. For example, returning all the updated records from the past or matching a particular set of events is not easily expressed as a path. With REST, it is likely to be implemented with a combination of URL path, query parameters, and possibly the request body. REST typically relies on few verbs: get, post, put, delete, and patch, which sometimes doesn't fit your use case. For example, moving expired documents to the archive folder might not cleanly fit within these verbs. Yeah, that makes sense. Fetching complicated resources with nested hierarchies requires multiple round trips between the client and server to render single views. Example, fetching content of a blog entry and comments on that entry. For mobile application operating system operating in variable network conditions, these multiple round trips are highly undesirable. Over time, more fields might be added to an API response, and older clients will receive all new data fields, even those even those that they do not need. As a result, it bloats the payload size and low and leads to larger latencies. RPCs and REST call comparison. Sign up, post, sign up. Okay, post persons in the REST. Okay, resign, post, resign. So this is like we are specifying the verb here and we are specifying the resource identifier here. Okay, read a person. Okay, I'll just look into this one here. Read a person's item list, read person's item list with the person ID. Okay, add an item to a person's items, post, add item to the list. Okay, persons 1 2 3 4 items. Okay, update an item, modify item. Okay, here, yeah, makes sense. I can totally relate to the uh, thought process that goes behind when an API or when an operation doesn't fit naturally to the REST convention. Do you really know why you prefer REST over RPC? Okay, this could be a good read, I guess. Debunking the myths of RPC and REST. What are the drawbacks of using REST? Crack the system design interview. Thrift. Why? Okay, security. Let's see. Let's close this one for now, and we can close this one as well. And then, do you really know why you prefer this one? Voices in my head. Okay, could be an interesting read. We can save it for later. Yeah. So yeah, I think we are done with one system design problem today. So we can revisit. I still haven't made up my mind here. Disadvantages of cache. Okay, let's close this one as well. So we are done with the pastebin for today. So let's look into what's next. There are two ways we can go about it. Okay, this is okay. So we have the next question here. We can come and try to solve that. Or okay, three ways. If someone has an opinion, I'll start another live stream in a bit. So either we can go with this question, or we can choose one of the random question here. Or another thing can be, okay, let's close this one. Another thing can be there is a system, design a system that scales to millions of users on AWS. This would be a generic read about any system. So we can go through this, or we can solve a coding problem. Either of those would work for me. But yeah, let's keep learning. This was a productive session, and I'm happy about how we are making progress now. I'll start. I'll actually get back in 30 minutes. I don't know if I want to continue the same live stream by having a break, or I want to start a new live stream. I might start a new live stream rather than keeping the people hanging around here. Uh, yeah, I'll start a new live stream, but I see there are many viewers concurrently watching now. If you are here, please make some noise and post some comments. How was it? Feel free to provide some feedback to me. How is it going, and how can I make it better? Even if there is one watcher or one viewer, I want to make sure that I'm providing some value, so we can keep it interactive, and we make sure that okay, everybody is getting something out of it and improving in our learning journey. So feel feel free to post comments, or please post comments about how I can improve and how we can make it more interesting, and follow along. Stay curious. I'll meet you guys in 30 minutes.